Assalamualaikum to you all. In my past episodes on gas laws, we treated gases as ideal gases that behave following the ideal gas law equation PV equals nRT. But there are physical conditions that gases tend to deviate from such ideal behavior. Find out what modifications or corrections are introduced to the ideal gas law equation so as to accurately compute the required pressure. So just hang on till the end of the video. Watch and learn. The extent of deviation of a gas from being ideal can be shown in a graph like the one given here. The ratio of the molar volume of a gas over the volume of an ideal gas at the same pressure and temperature is called the compressibility factor, denoted by capital Z. So the compressibility factor, capital Z, of a real gas is just equal to the ratio of V sub m divided by V, where V sub m is the molar volume of a real gas at the same pressure and temperature, and V is the volume of an ideal gas at the same pressure and temperature. All right? So, if the compressibility factor of a gas is exactly equal to 1, that means the gas is an ideal gas. And deviations from Z equals 1 means that the gas is not behaving like an ideal gas. All right? So if this compressibility factor for some gases, all right, are plotted against the amount of pressure, all right, such gases like nitrogen gas, methane gas, hydrogen gas, oxygen gas, and carbon dioxide gas, we come up with this graph, all right? And it is pretty obvious that at higher pressures, these gases tend to deviate, all right, from having compressibility factors equal to 1. Based on what we know about the ideal gas law, the molecules of a hypothetical ideal gas have no significant volume and that they do not attract or repel each other. In general, real gases approximate this behavior at relatively low pressures and high temperatures, right? At high pressures, however, the molecules of a gas are crowded closer together and the amount of empty space between the molecules is reduced. At these higher pressures, the volume of the gas molecules themselves becomes appreciable relative to the total volume occupied by the gas. The gas therefore becomes less compressible at these high pressures and although its volume continues to decrease with increasing pressure, this decrease is not proportional as predicted by Boyle's law. At relatively low pressures, gas molecules have practically no attraction for one another because they are, on average, so far apart, and they behave almost like particles of an ideal gas. At high pressures, however, the force of attraction becomes significant. This force pulls the molecules a little closer together, slightly decreasing the pressure if the volume is constant or decreasing the volume at constant pressure. And this change is more pronounced at low temperatures because the molecules have lower kinetic energy relative to the attractive forces, and so they are less effective in overcoming these attractions after colliding with one another. An equation that better approximates gas behavior than does the ideal gas law is the van der Waals equation developed by the Dutch scientist Johann van der Waals in 1879. The van der Waals equation improves upon the ideal gas law by adding two terms. Alright, from the original ideal law equation, PV, the product of the pressure and the volume equals N capital R capital T, alright, is modified into alright. So two terms are added, alright. The first one uh, is to account for the attractive forces among the molecules, right? So this correction, which is expressed as the constant A times the square of the number of moles divided by the square of the volume, right? This is the correction for molecular attraction, and it is added to the pressure P. The second correction, right, is to account for the gas or the volume of the gas molecules. Okay, it is expressed as the volume V minus the product of NB. N, of course, is the number of moles of the gas, and the constant B, right? These two, van der Waals constant, okay, the constant A pertains to the strength of the molecular attraction of the gas, while the constant B refers to the volume of the molecules of a particular gas. Note that when uh, the volume V or capital B is relatively large and the number of moles small n is relatively small, both of these corrections or correction terms will become negligible. Again, at higher value of the gas volume capital V, okay, and a small value of the number of moles, small letter n, okay, would mean that these corrections become negligible, and that this van der Waals equation simply reduces to the ideal gas law PV equals nRT. In short, the van der Waals equation is actually just a modification of the ideal gas law. Okay, PV equals nRT with corrections made on the pressure and the volume. All right, and is considered accurate when the pressure is or the pressure of the gas is high and that the temperature of the gas is low. The van der Waals constants A and B of some common gases are given in this table, right? And we are highlighting these constants for the gas carbon dioxide because we will be using these constants in our next example problem. So the van der Waals constant A for carbon dioxide gas is 3.59 liters squared atmosphere per molecule or per mole squared, right? So this is just one commonly used unit, all right, for this van der Waals constant. And for constant B, the value of or for carbon dioxide is 0.0427 liter per mole. So our example problem is a 0.245 liter flask contains 0.467 moles of carbon dioxide gas at a temperature 159 degrees Celsius. Calculate the pressure, letter A, using the ideal gas law, letter B, using the van der Waals equation, and letter C, explain the reason for the difference in your answer to letter A and letter B. So as usual, let's identify the given information in this problem. The volume of the gas is denoted by capital V equals 0.245 liters. And it has a temperature, capital T, equals 159 degrees Celsius, which when converted to Kelvin, that is equal to 432 Kelvin. And likewise, we are given the number of moles of the carbon dioxide gas equal to 0.467 moles. And our target variables, first, we have to find the pressure, okay, small letter p, using the ideal gas law equation, PV equals nRT. And for letter B, okay, we also compute the pressure, but this time using the van der Waals equation, right? Which was presented earlier, but the working formula for that is given in this equation. The pressure P is equal to nRT, all right? The product of the number of moles of the gas multiplied by the universal gas constant, capital R, and the Kelvin temperature that is given. So their product is to be divided by the quantity, capital V, which stands for the volume, minus the correction, and V, or the product of the number of moles of the gas and the van der Waals constant B, right? So after getting the quotient for this term, we will deduct this one, okay, which is the ratio of the product of the constant A and the square of the number of moles, or AN squared, and that will be divided by the square of the volume, right? So you should remember that the temperature, capital T, given is in Celsius, all right? That is the reason why we have to convert it to Kelvin, because in using both equations, PV equals nRT and the van der Waals equation, both of them requires that the temperature, capital T, must be in Kelvin, right? So, as presented earlier in the table for the van der Waals constants of some gases, so we take note that the constant A for carbon dioxide is equal to 3.59 liters squared atmosphere per mole squared, and the constant B for the same gas, carbon dioxide gas, it is equal to 0.0427 liters per mole. Moving on now to our computations. For letter A, finding the pressure P using the ideal gas law equation, P equals the product of nRT divided by the volume V. Plugging in the given data into this formula, we get P equals 0.467 mole, all right, times the value of the universal gas constant, capital R, 0.0821 liter atmosphere per mole Kelvin. And then times the Kelvin temperature, 432 Kelvin, right? So once we get the product, that will be divided by the volume, 0.245 liters. So when you do our math, we get the pressure P equals 67.6 atmosphere. Take note, the unit mole cancels out. Okay, the unit per volume liter and the temperature unit Kelvin are also cancelled, leaving behind the expected unit for pressure, which is atmosphere. Next, for letter B, computing the pressure, but this time using the van der Waals equation, all right? In as much as the equation is quite lengthy, what we'll do is to calculate each of these terms, starting with the product nRT, right? So that means the number of moles of the gas, 0.467 moles, times the universal gas constant, 0.0821 liter atmosphere per mole Kelvin, and times the Kelvin temperature, 432 Kelvin. So again, doing our math, we will get that product nRT equals 16.6 liter atmosphere, right? Take note, the unit moles and Kelvin have already been cancelled. So we are only left with liter atmosphere. And then the term quantity V minus NB, all right, that would be the volume of the gas, 0.245 liter, minus the product of the number of moles and the constant B, or 0.467 moles times 0.0427 liter per mole. So as usual, when you do our math, we get V minus NB equals 0.225 liter. All right, so for the term AN squared over V squared, we have 3.59 liters squared atmosphere per mole squared times 0.467 mole squared, all right? And we divide that by the square of the volume, 0.245 liter. So doing your math carefully with the help of your calculator, we get the value of this term, AN squared over V squared, equal to 13.0 atmospheres, also in three significant figures. So this brings us now to our final computation for the pressure P. All right. Since we already got earlier the value for the term nRT, which is 16.6 liter atmosphere, so we just divide that by the term V minus NB, which we also have obtained earlier. That is 0.225 liter, and their quotient, okay, minus 13.0 atmosphere. This is the value of AN squared over V squared. All right. So simplifying, we get the value of the pressure, okay, equal to 60.8 atmospheres. Right. So comparing this with the value of the pressure using the ideal gas law equation, all right, 67.7 atmospheres. So there really is a difference. And in answer to the additional question letter C, right, what is the meaning of the difference in the pressure? Well, the difference, of course, is due to the fact that the van der Waals equation takes into account the volume of the gas molecules and the intermolecular attractions, right? Based on the ideal gas constant or ideal gas law equation, all right, these conditions are considered negligible, all right? In the ideal gas law, the volume of the gas molecules is considered almost zero, in that the molecules do not interact, they do not attract, they do not repel, all right? But in here, using the van der Waals equation in our computation for P, we in fact considered, all right, the volume of the gas molecules as well as the presence of the intermolecular attractions. And that explains why there is a difference in the values of the pressure. So that's it, we're done. All right. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.